Hi everyone, Mr. Boltri here bringing you video 2.2 where we're going to talk about Newton's three laws. So to do this, we're going to talk about the third law, first law, and then second law. And I know it's a weird order, but just trust me on this one. So first, let's start talking about the third law. And to do this, let me show you a quick example. So in this example, I have two buggies, one which is loaded up with a bunch of mass and one which has no mass, no extra mass at all. And on each is a little force sensor, and then I'm going to smash one of the buggies into the other buggy, just like this. Okay, so with that example, and I'll show you one more time, my question is, how much bigger is the force from the heavy buggy on the light buggy? Like 2 times as much, 3 times as much. So I'm going to take the heavy buggy and then push it at the light buggy. And how much bigger is that force? Okay, so the answer might be surprising to you. This is what the force diagram looks like, or the readings on the two force probes. Anyway, so this is the force probe of the big car. This is the force probe on the small car. And what do you notice about these two force diagrams? It might be surprising because oftentimes people want to say the heavier car exerts more force. It's also the more active car because the other one's just like sitting there. So they want the red spike to be way higher because there's more. They think there's more force there. But the reason why I'm starting with Newton's third law is because it's just one of those rules. This is just the way the universe works. You may have heard it said this way: every action has an equal and opposite reaction. And that's a fine way if you want to remember it that way. I think that there's a better way to remember it, and I'll tell you why. Because we're not talking about actions here. I think of action as like dancing or playing football. We're talking about forces specifically. Equal what? Opposite what? And reaction, when I think about reaction, I think about like if somebody posts a video, then I might post a reaction video like the next day or 2 days later. But when we're talking about this, they occur at the same time. So the word action and reaction are not the best words to use here. Instead, when I think about Newton's third law, I think about paired forces. I call it the paired forces law when I'm talking with my freshmen. So the way paired forces work are when one force occurs, always, every time, this is just how forces operate. When one force exists, another force also exists at the same time. So if the heavy cart exerts a force on the light cart exerts a force right back on the heavy cart. They are equal in magnitude, opposite in direction, and occur at the same time. And that's a little bit weird. It doesn't seem like that should be true. It seems like the heavy cart should exert more force than the light cart. That's not the way it is, and I'll explain why using Newton's second law. But for right now, this is just a law. This is just the way that it works. This is just the way that it is. And it is this way every single time with absolutely no exceptions. Not any that we've found so far anyway. So this is Newton's third law. Oh, and here are two little pairs because it helps me to remember the paired forces law. And the only thing that's wrong about this image is that they are not equal in magnitude. One is a little bigger than the other. But besides for that, they are opposite in direction and pretty identical. And they're there at the same time. So now let's do the same thing for Newton's first law. I have a similar example here where I have a cart which is attached by a long string, which you can see down here, to a spring, which is just going to be a little weight to drag it. So what I'm going to do right now, it's stationary, and then I'm going to push it in the negative direction with the ruler. Then I'm going to stop pushing it, and it's just going to sort of like slide along the track until we run out of slack here. And then it's going to start pulling the mass, and then it's going to stop at the end. So let's watch the video just so you believe everything I just said. Okay, so I push it, stop pushing it, it's coasting, and then it drags the weight and comes to a stop. So what I'm going to ask that you do is just to make a prediction, and you should be able to do this from our kinematics unit. What is the position versus time graph going to look like for A, B, C, D, and E? And also, for each A, B, C, D, and E, I would like for you to draw the force diagram for the forces acting on the cart. I'm going to pause here to make sure that you have time to do it. You might need to pause the video just to give you time to do the position versus time graph and the force diagram for A, B, C, D, and E for the forces acting on the cart. So here's what it looks like. So in A, it's stationary. It's over a meter away. In B, it sort of has this curve because my pushing caused it to speed up. And then it's just coasting along. Then it is dragging the weight and slowing down. And here it is stationary again. So if we look at the force diagrams, there's just a force normal, force gravity here. And also in E, sort of similar. Here, the force applied, I did push it in the negative direction, so the force applied is in that negative direction. And then here, the force tension is in the positive direction because the weight was pulling it in the positive direction. And so here's the really tricky one. People want to say that there's some sort of force applied here because, well, I pushed it. So in order for it to be moving, there has to be some force to keep it moving. But you'll notice I was very clear that when I pushed it with the ruler, I pushed it and then I stopped pushing it. Let's watch that actually one more time. So I push it and then I stop pushing it. And I'm trying to be very clear about that because in part C, I want you to see that as it's coasting along the track, there are no pushes and pulls in the horizontal direction. So it's coasting along the track with no pushes and pulls. So what conclusions can we make from this graph? Well, we see that every time the graph is curvy, which means that there's some acceleration, there is a horizontal force. And every time the graph is linear, either horizontal or just linear, we see that there are no horizontal forces. So from that, we get Newton's first law, which is an object at rest will remain at rest, and an object in motion will remain in motion with the same speed and moving in the same direction unless acted on by an unbalanced external force. So that's a mouthful. Again, there's a way that we can clean this up, but this is probably the way that you've heard it before. The way that you can clean it up is, well, if it's at rest or same speed, same direction, there's a word that we have for that. You can just say an object will maintain a constant velocity unless acted on by an unbalanced external net force. So we'll talk about more what unbalanced external net force means, but it basically means pushes or pulls that cause it to change its velocity. So the word net is a fancy word for like if you cast a net out into the water and you pull it back in, you're going to get everything that's in the water. If you're trying to catch salmon, you might catch some salmon, but you might also catch some tuna and some trash. So you're going to pull in everything that's in the water. And the net force works the exact same way because we're looking at all of the forces that are acting on the object. So for example, here, the net forces in the horizontal direction is just the force applied because there's no force to the right. So the net force in the horizontal direction is just going to equal the force applied. But in future examples, we're going to have multiple forces acting in the same plane, either horizontal or vertical. So then we're going to get a more interesting net forces. So this is Newton's first law. It basically says things will maintain constant velocity unless acted on by a net force, non-zero net force. Here's kind of a way that you can visualize this, because if the forces are balanced, which is a fancy word for saying that the net force is zero, all the upward forces equal all the downward forces, or left, right, then it's going to move with a constant velocity, either stationary or just sort of coasting along at a constant velocity. If the forces are unbalanced, maybe more to the right than to the left, or what have you, then it's going to have a changing velocity. It's going to experience an acceleration. So this is a nice visual for Newton's first law. And Newton's first law is also sometimes called the law of inertia, which may or may not be a word that you're familiar with, but inertia is a property of matter, which basically means that it's not a force. It's connected to mass, which is also another property of matter, whereby objects tend to maintain their velocity. And just Newton observed that objects do this, they maintain the velocity. He named Newton's first law after it. Because he called it the law of inertia. He invented this idea of the word called inertia, which is that objects maintain their velocity. Objects that have mass or matter, because those two things are connected, related. Okay, now, Newton's second law. That's the one that we did in class today or yesterday. Depends on when you're watching the video. But basically, it's trying to quantify the relationship between force, mass, and acceleration. And it looks like this. Notice here that we have the vector signs on force and acceleration because if we read this whole paragraph, the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force and in the same direction as the net force. That's what the arrows show. They're vectors, and they show that this vector is in the same direction as this vector. And it's also inversely proportional to the mass of the object. So this is just a big paragraph to say that this equation is true. And we showed this equation in class. So it shouldn't be a surprise to you. But there is one word in this that I would like to draw your attention to. It's that pesky net, because it's not often that there's just one force acting on something. So we have to look at the net force acting on an object. So this sigma means the sum of all the forces, which is just another way to write net force, or you could just say F net. But those are very important because you can't just look at one force and try to predict the acceleration based on that one force. So here, these are the three laws: Newton's first law, second law, and third law in visual form. We have balanced forces equals constant velocity, for the net force equals the mass times the acceleration, and the paired forces law. And I love this because the Newton's second law, to me, just really ties everything together, because it's a quantification of Newton's first law, because balanced forces, that means the net force is going to be zero. So zero net force gives us zero acceleration. That's just how the equation works. And then unbalanced force, that's a non-zero net force, gives us a non-zero acceleration, which is changing velocity. So Newton's second law is basically just a quantification of Newton's first law. And then, like I told you at the beginning, how does it make sense that let's say, how does it make sense that the Earth and the Moon are exerting the same gravitational force on each other? Because it seems like the Earth should be exerting way more gravitational force on the Moon. But the trick here is because of inertia. The more mass you have, the less your acceleration is going to be caused by the same net force. So the Earth and the Moon are causing the same net force on each other, but because the Earth has way more mass, the acceleration of the Earth caused by the Moon is way smaller. But because the Moon has less mass, the acceleration, the mass is smaller, so the acceleration has to be bigger due to the same net force. So I just really love how these three things are connected to each other. First, the second law quantifies the first and explains the third. So that was kind of a crash course and hopefully a reminder as to Newton's three laws. And we're going to do practice problems in class and answer questions. So do let me know if you have any questions. And I'm looking forward to practicing Newton's three laws together with you all of Unit 2. But for now, this is Mr. Boltri wrapping up video 2.2 on Newton's three laws. And as always, go Bears.